So who's problem number one? You guys are on deck for your presentations.
I don't think we decided. Do you guys want me to screen share or someone else?
So our problem was problem one, and we were just comparing two circuits.
Our goal was to compare the circuits, and the two circuits we had to compare, one was series and one was parallel. They each had 3 light bulbs and 3 batteries. Yeah. Oh, and this is the drawing of it, and then we have what it looked like when we actually built it.
All right, and then we need to draw the starburst and arrow tails. So figure 1 was in series, so it wasn't very bright because the one arrow tail had flow through all 3 bulbs. That's why there's only 2 starbursts here. And so for figure 2, it was in parallel, which means that there are more arrow tails to start, with 6 arrow tails originally. They split into 2 per bulb, which is much brighter than 1 arrow tail, which is why we put 4 starbursts in figure 2.
For figure one, the positive terminal is red and then the negative is blue. We know for a light bulb to light up, it has to have an equal jump in pressure. So the wires touching the middle light bulb are yellow with a little bit of orange and a little bit of green. For parallel, the wires on the top are red and then the wires on the bottom are blue. And the light bulb lights up because one side is positive and one side is negative. And parallel circuits are 3 individual circuits connected to the same power source. So they don't actually interact with each other. And that's why they don't change colors.
So why do the bulbs glow? The bulbs glow because there is a completed circuit and electricity is able to go through the light bulbs. Which circuit has brighter bulbs and why? B is brighter than A because B is in parallel and while A is in series.
And then for the last part, we had to compare 2 other figures that were different from the first ones, but we had figure 2 and figure 3. And as you can see, they're both in parallel. They both have 3 batteries and 3 light bulbs. And so we decided to build it too and show the picture of what it was supposed to look like. And we decided that looking at the picture and knowing the color coding that the brightness would be the same, because if you were color coding, they would have blue on the bottom from coming from the negative side, because there's always a wire touching another wire that would turn the wire blue, and same on the top. And then because it only goes through 1 light bulb each, it would just be red to blue on both circuits, as Hayden explained about what parallel circuits are. Yeah, thank you.
Awesomeness. Thank you so much. Questions? Group 1, what was the favorite part of that particular why did you choose that question, I guess, is my question. Why did you guys choose that question? I guess you didn't really choose that question. I set you up in that question, but you did vote for that question. So why did you vote for that question?
I think it's pretty interesting just comparing 2 circuits, and comparing like all the aspects of it, the arrow tails, the starburst, and then the color coding.
Okay.
Yeah, I also feel like this question did like a good job bringing together like a lot of the stuff we've learned and like really focused on this semester.
Okay. Thank you for that. Group 2. Where are you at?
All right. Should I also share my screen or? Okay, I'll share my screen. Okay. Actually, I didn't think about this, but I can't see the script while I'm screen sharing. So I will.
I can screen share.
Okay.
Oh goodness. I'm so this is not working out as planned. Okay. That's weird. Okay. Can everyone see that?
Yep.
Yep.
All right, should I start?
Go ahead.
Nice. Okay, so this is our project. For number A, the negative end will have more charges than the positive end because the capacitor doesn't allow the electrons through after filling up on one side. So basically, they'll build up on the negative side because the circuit is going from negative to positive. The electrons, the negative electrons will flow through the wire onto the negative side of the capacitor. And the light bulbs only work for a short time when the capacitor is still charging, but allows for electric flow. So that's where we're at.
Let's see. Can someone else share their screen? Because now I can't really see what I'm supposed to be looking
Sure.
at.
Yeah.
Alrighty. Okay, so according to the problem, this would be an example of a correct LOL diagram for our system of the circuit. This is for part B.
Sorry.
Oh yeah, there we go. That's the right slide. And as it says in the problem, the system happens to be isolated. So this means it'll include the wires, the battery, the light bulbs, even the air around it, I guess. So to explain this LOL diagram, we'd start off with no potential electric energy. And this becomes 1 cube of potential electric energy at the end from the capacitor becoming charged and storing energy inside it. It starts our LOL diagram also starts with 4 blocks of chemical energy, potential chemical energy, I should say. This becomes only 2 blocks because the chemical energy is stored within the battery and the battery is discharging. And at the beginning of the process, the system holds only 1 block of thermal energy, and this turns to 2 blocks from the heat of the light bulbs in the circuit.
All right. It's if someone else can share.
This is complicated. Just a moment, please.
Okay. So for C, this circuit is basically the same as the first circuit. It's very similar, but the difference is that the batteries are flipped, so that the negative side is where the positive was and the positive is where the negative was. This really only changes where the electrons build up. So in this case, they'll build up on the positive side, whereas previously they would have built up on the negative side. I also have the next one, which is the same slide, actually. So same circuit, again, comparing it to the first slide, the positive side will have more pressure than the negative side. So this is also D now. And because the batteries are flipped, previously the electrons would have built up on the negative side, but now they're building up on the new negative side of the capacitor because it's all flipped. Trying to get to the things.
All right, so this is our new circuit, and this is for problem E. This circuit would basically not allow the capacitor to be charged again if it was discharged. As you can see, if you look at the wires connecting the two battery packs, it connects two negative ends of the battery to the circuit. This means that since there's no positive end of the circuit, there will be no electric flow, and thus the capacitor cannot become charged. And if we were to plug in light bulbs, I'd imagine they wouldn't be able to light or function either. So basically, this circuit just wouldn't function as a whole. Next slide, please. This is problem F. This circuit, however, would allow the capacitor to be charged again. Unlike the last circuit, this circuit has both negative and positive end, allowing electricity to flow, and they're connected together correctly. If you were to place an uncharged capacitor in the circuit, it will quickly soak up as much current as it can hold. In fact, the capacitor would charge much more quickly than normal due to the amount of electricity provided by all the batteries. As for which side will hold the electricity, we can predict that the top side, the negative end will, going off of the assumption that electricity will move from negative to positive end. The top part of the capacitor will briefly allow electricity to pass before filling up one side and halting the flow. That was our last slide. Thank you guys for watching. That was our presentation.
Thank you.
Can you guys see that?
We can see it great.
Okay, so we were, for our final project, given problem 3.
These are the guidelines for problem 3, and the guidelines are to create an interesting circuit, including what materials we need to include in the circuit. Next slide. This is our circuit, and for our circuit we use 3 batteries, 2 round bulbs and sockets, 2 long bulbs and sockets, 1 capacitor, and 9 wires. The round and long bulbs are a parallel circuit, and the round are a series circuit, and a long and long are a separate series circuit. So this is us charging the capacitor. As we are charging it, the long bulb starts to dim, but the round bulb stays brightly lit.
In this circuit, the round bulbs were brighter than the long bulbs because less electrical current went through the wires of the long bulbs. We gave the round bulbs 6 starbursts and the long bulbs 2 starbursts. We're using the conventional current, which is the current that starts at the positive end of the battery and goes clockwise. The circuit started with 4 arrow tails that started at the positive end of the battery. And when the current split, 3 arrow tails went to the round bulbs and 1 arrow tail went to the long bulbs. This is because the round bulbs have less resistance, so more current will go to the round bulbs because it's an easier path to take, and less current will go to the long bulbs because the long bulbs have a greater resistance, so it'd be a harder path to take. At the end of the circuit, there were 4 arrow tails going to the negative side of the battery. Next, we had to color code our circuit. So we used the color key that we had learned in class, with the red being the highest pressure, descending down to blue with the lowest pressure. So we started by color coding the wires out of the positive side of the battery red, and continued with the red until we ran into light bulbs, and we used the same system for the blue wires coming out of the negative side of the battery. For the 2 round light bulbs, we know that the jump of the pressure between the 2 has to be equal. So we use the yellow wire coloring because it's evenly in the middle. And then for the two long bulbs in the capacitor, the top wire is a yellow-orange mix and the bottom wire is a yellow-green mix, again, to evenly split the difference. For part E, we were given a circuit and we had to color code it. And this circuit has 2 batteries, 13 wires, 2 round bulbs, and 1 long bulb.
And so starting off when we were color coding it, we began at the positive side of the battery and put a red wire, and then all wires touching that same red wire also became red. And then we just did the same thing for the negative side of the battery, but with the color blue. And then kind of in the middle of the circuit, we came across a problem. As you can see, like that one wire is red and blue, and then, but that can't happen because a wire can't be 2 colors. So it has to be either red or blue. And then so we decided that the circuit would either have to be all red or all blue. And then either way, none of the light bulbs would light up. But then later we found that was incorrect, and Natalia will explain that.
Yeah, so when we created a digital version, we can see that none of the light bulbs lit up. And then there was also a short circuit that caused the batteries to light on fire. But when we created it in real life, we saw that the round bulbs lit up like a tiny bit. So we came to like a decision that the wires have to have some sort of resistance.
Yeah, and then to sort of fix the circuit with the online version where the wires don't have resistance, we decided to add in some sort of resistance in between that one wire. So we just put a round light bulb in between that one wire. So there was a red colored wire and a blue colored wire. Yeah, thank you. Any questions?
So many. I have so many questions. First of all, thank you. That was a really great presentation. Let's see, can we go back to, where do I want to go back? Can somebody show your side? Can you just go back? I have some questions. I mean, again, it was a great presentation, and you had a really complicated problem. So, yeah, so actually, yeah, let's do the one where you're showing your circuit. Yeah, one more. One more. Beauteous. Thank you. So can you Thor, talk to us a little bit about when is, so it sounds like in your movie, when you made the movie of this thing, it sounds like the light bulb eventually stopped, the long bulb stopped glowing, right? Is that correct? Or did they continue glowing? The round bulbs glowed all the time, but did the long bulbs stop glowing at some point?
Yeah, when they were charging the capacitor, they like slowly dimmed until there was no light.
There was no light. So the question is like, if there was no light, when is this diagram that you made is totally great and it's valid. The question is, when is that diagram of, like, is that when you just plug in the circuit? Is it halfway, like a couple seconds after you lit the circuit? Or is it like minutes after you hooked up the circuit? Like, or would you expect this diagram to change over time?
I think of this diagram is like right when we connected it, and then I guess it would change because if the long bulbs dimmed, there'd be like the dotted lines, I guess. Yeah.
Can we move one slide down? The next slide, I guess, the color coding. Yeah, so how would you expect the color coding? I understand why there's yellow between the 2 round bulbs, right? And you need, so when the light bulbs turn off, what would be the colors in that part of the circuit? what would be the, when the long bulbs turn off, what would be the color of the wire just underneath the long bulb, the top long bulb?
Would it be red, like continuing down because like the light bulb isn't like taking in the energy anymore?
Yeah. Why is the light bulb not taking energy anymore? Or why is it becoming red? Like what's happening?
Well, it already like lit up and then it dimmed down through the charging process.
It dimmed out to it, and then once it's fully charged, when the capacitor is fully charged, what do you know is going to happen? Like what is going to be the pressure at the top of on the plus side of the capacitor? What's going to be the color? What should be the color?
Red, right?
Yeah, whatever the color of the battery was, because that's what's charging up your capacitor, right? So at the end, you're going to get red on the top half, and then you're going to get blue on the bottom half. I mean, this is great. Like this is like an intermediate step. What would be the color? What do you think would be the color of the wire? Just like literally the moment you hook, so you have your whole circuit, the battery's unhooked, you hook your battery. Right at that moment, the moment you hook the battery, what should be the color of the wires between the two long bulbs before it charged? Anybody? What was the color of the capacitor when it was uncharged?
Yellow, right?
Yellow. Yeah, should be yellow. So the moment you hook the battery, your capacitor is yellow. And then what it has like red on one side and yellow on the other. So the light bulb becomes super bright because there's a big pressure difference. And then the pressure on the capacitor starts to mount as charges arrive, right? So it goes from like yellow to a yellowish orange to orangish yellow, right? And at some point, it's going to keep on going, orange, orangish red, and then it's going to become completely red. As the pressure mounts on your capacitor, there's going to be less and less flow in that part of the circuit. Your light bulbs are going to get dimmer and dimmer and dimmer. Eventually, the capacitor becomes red on one side and blue on the other. At that point, there is no flow in that part of the circuit. How many arrow tails are going to be on the left side of your circuit then? When your capacitor is fully charged, what should be the arrow flows through the round bulbs?
Uh, 4, right? Because none are going through the capacitor.
Exactly, right? So this is a really interesting, and this is so group 3, you did a really nice job because we had never talked about the charging of the capacitor, like specifically what happens over time. And so what you did is you correctly identified the sort of the intermediate, like when the light bulb are not super bright, but they're not dim, like somewhere in the middle. That's what your diagram would be of, okay? Which was great. Okay, and then now can we go to the color coding for the last problematic short circuit thing? There we are. So, oh, actually one more one more. Okay, so you introduced the resistance in the middle of your wire, which is the only way you can make sense of this circuit, right? Question for so first of all, can somebody not in group 3 summarize like what the issue was? What was the issue in this circuit? Anybody? Yeah, Hillary.
There's different resistances, right? Because of the long light bulb.
So there are different resistances, right? But before they put the light bulb in that third branch there in the middle, right? What was the issue? I believe it was Natalia who was explaining what the issue was. What happened?
You want me to explain it? Because I thought you said someone. Okay. So basically when we didn't have that, like there was half red, half blue, and that can't happen. So it could either be like all red, and then if it were red, then that like the third wire would be red, and that would be touching all the other wires, so that would all be red. And since it's all red, then that like won't light up, and then it would be the same for blue.
Got it. So you have a short circuit. The short circuit touches both sides of the battery, and the circuit and the wire cannot be both and red and blue at the same time, right? So this is where, and so you came up with a really clever solution to say, yeah, I don't know, like the only way this can make sense is if I put a light, not a light bulb, but like a resistance, right? Some resistance in the middle of the circuit. And that would allow it to separate sort of the blue C from the red C. Totally makes sense, right? What you're saying though is a little bit more, what you're saying though is a little bit different. What you're saying is, in order for your circuit to make sense, the wires themselves need to have a resistance, right? That's what you said. The wire needs to have a resistance, but not just that wire, right? All the wires need to have a resistance. If all the wires have a resistance, then how would you change the coloring of your circuit? Because what's going to happen, right? What's going to happen is not only are you going to have a resistance on that branch, but let's look at the first round bulb, the one the most to the left, right? So that's a round bulb, but the wire going like diagonally up, that also has a whole bunch of resistance throughout. The wire connecting that at the top also has a bunch of resistance. The wire going straight up from the battery also has a bunch of resistance. So how would you change the color coding to accommodate for this? Natalia.
So at the beginning it would be like a really like red, and then as it goes on, it will get like lighter.
Yeah, that's actually like finding some kind of way to make like, so it'd be interesting. I don't know exactly what that would look like, right? But what that would mean is that it would be red, and becoming less and less red, maybe even like orangish and yellow, right? All the way up to actually probably not yellow, because you still need a difference of color between like on either side of the resistance. So maybe up to orange. So like a red to like a red to a reddish orange to a orangish red to an orange maybe. And then at the light bulb, then you switch to like a greenish blue, a bluish green, right? And then all the way back to blue. But what's interesting is that the wires don't have just one color. They have now you have a rainbow of color, right? Because what you're including in this is the fact that every single inch of that wire has a resistance, and therefore there's a little bit of a pressure drop across each inch of the wire all the way to the light bulb, which has a big drop of pressure, which is really interesting, right? That's something that we haven't thought. Group 3, really nicely done. That was a really beautiful presentation. Thank you. Group 4, you are up. And now for the creative process, group 4.
All right, I can share the slides. All right, so we're group 4, and we did problem 4, which is basically about conductors, insulators, resistors, and lightning. So.
Okay, so basically this is problem A1, and basically you hook up a piece of lead to the wires in the two wires in the circuit, and you see if it makes the lights light up. So basically the graphite and the pencil, and it's asking if it's like conductive. So basically the graphite and the pencil is conductive, and it makes the lights light up. So meaning, yeah.
So for this one, it was asking if air is an insulator, and air is a really good insulator because electricity can't really pass through it. unless there's like a massive amount. And when current flows from the positive end to the negative end, it does not interact with there because air rarely conducts electricity, and it only conducts electricity on rare occasions, which we will talk about later.
All right, so air is not usually a conductor, then why does lightning exist? So air can behave as a conductor, like given a massive amount of current, and air doesn't like conduct electricity in the way that metals do. It relies on ionization for it to become a conductor. And ionization is basically when like a high amount of energy causes uh, an electron and like an air molecule or air atom to like discharge. So the electron's discharged, and basically the electrons aren't really like bound to the air atoms, I don't think. So the electrons cause like the formerly insulating air to become like a plasma, which is conductive, and yeah, so then air can be used as a conductor.
Okay, so basically you would need an enormous amount of energy in order for a capacitor to act as a conductor because there's an insulator between the two plates in the capacitor, meaning that in order for a charge to flow through, you would need an enormous amount of energy. So, yeah.
So why we're saying that electricity needs an enormous amount of energy to flow through a insulator is because electricity can flow through anything given the like right amount of energy or like a massive amount of energy depending on what the material is. So depending on what the material is, it could either melt, catch on fire, or shatter because like if you have enough force with electricity, it's possible for any of those to happen.
So the last question was just asking, so what is myelin? So myelin sheath is essentially a brain insulator. So it covers your nerves and it just makes sure that signals don't go to the wrong place. And it protects your nerves from different electrical impulses within your brain. Okay, so, and the last question was asking what MS was. So MS is essentially when those connections or when that insulator is degraded and it doesn't work properly. So nerve impulses within your brain can affect nerves they weren't intended for, which can lead to things like numbness in your arms and legs, or like not moving your hands properly, or not being able to balance right. And it's essentially it's the insulator of your brain, and when it's damaged, the current just goes wherever it feels like.
All right, that's the end.
Cool. Questions for that group? That's like the, thank you, good job. That's the one that we have the least amount of background on, so I'm hoping there's gonna be some questions. Anybody? Yeah, Hillary?
I mean, it seems like this kind of exists for everyone's, but it felt like a lot more like answering questions, which it kind of was, than like a flowing presentation about something, which I guess is probably due to the fact that it is answering questions. But I don't know. Just thought I'd point that out.
Interesting. So maybe doing more of like transitioning from side to side. Interesting. Any questions about the topic itself? About myelin, about what's happening in the brain, about nerve? Yeah, Kian.
First off, I'd just like to say that was a really cool presentation to look at, especially since a lot of us were like less aware of what's going on beforehand. But so just to clarify, what's happening in the MS is like, since your brain is really just sending off like small electrical signals, right, to like control your body movements, Can you clarify that one more time? What's going on there? Because it's a little complicated to me.
Yeah. Your brain uses electrical impulses to like make your nerves do stuff. So it sends a signal, which is in the form of electrical impulse to make a certain nerve do a certain thing. And MS is basically an insulator. So it stops those signals from going to the wrong place. So if you wanted to like move your arm, that's a specific group of nerves somewhere in your brain, and that signal has to travel across your brain. And you don't want it to hit the wrong things because then you'll move the wrong limb.
All right, got it. Thanks for clarifying.
Hold on, let me share something because I can help there also. Let's see if I can do this. Screen, broadcast. Can you guys see this page?
Yes.
Cool. So the neurons in your body look something like this, right? The part on the left, the diagram on the left, actually yeah, so that would be in your brain, right? That would be the part that's like in the white matter in your brain, the gray matter in your brain. And then you see the cell is a nucleus, and the cell has this enormous long arm that it sends out called an axon, right? And it's the axon, for all intents and purposes, is like a wire, right? So think of it as like a metal wire. It's not made of metal, but it's a wire, right? And then the wire extends pretty much throughout. I mean, it could be it could be super short and connect to other cells in your brain, or it could be a neuron that extends all the way from your brain to your arm, right? To your hands, to like because at the end, the axon terminal, the bundle, right, could be like where like you feel things, like this could be connected to your arms, to your muscles that force your muscle. Like, for example, if you feel something is hot, you remove your hand, right? The movement of your hand requires a message, right? And at the end, the message will be delivered by that axon terminal bundle to your muscles that would make your hand move away from the fire. And you see the myelin sheath is that sort of like, it's that coating that surrounds the wire. Now, if the wire was not coated, it would be the same thing as if you had two metal wires touching, then it would be, right? If two metal wires were to touch, then you would have a circuit, and then the electricity would go through all the different wires that touch. But because the wires are separated, right, they're insulated by this myelin sheath. The message only flows down one wire, so you're guaranteed that if you want to remove your right hand from the fire, it's not going to both your right hand and your left hand and your right foot, right? It's just going to your right hand. Also, what's interesting is that the way the current travels into a neuron, you see how there's a thing called the nodes of Ranvier. Those are little, like, so think of the myelin as like a little like protective something, right? And at the end, but it only has so much length to it. And then between two myelin sheath, there's this node, and the message goes from node to node to node to node. And what's interesting is that the longer the spacing between those nodes, the faster the signal is transferred. So when the myelin sheath gets reduced in size, then there are more jumps happening. And so the signal, not only is the signal possibly leaking, but the signal is also not going as fast, right? So that is what is happening. Stop sharing. That is what's happening in a neural network, which is totally fascinating. Yeah, so let's stop. You attempted in broadcast. Okay, whatever. So that was just a little bit of background, but it's super fascinating, and the physics and the biology of how neurons work is totally interesting, and you guys will see that in biology 2 years. Let's see. Stop recording. There we are.